Okay, I guess we can start. Um, okay, Toma, can you hear?
Yep, just fine. Thank you.
Um, they, I am also equipped with my PC pencil, but let us still try to start with the big screen. Difficulties, and then I switch over. Now, last time we finished, not finished, we discussed the started to discuss vorticity and transport of vorticity by fluids. And I learned that turbulence is actually a mixing of vorticity. And the transport equation is such that vorticity flux is conserved. Similarly to magnetic flux, and in the case of magnetohydrodynamic turbulence. And it makes it similar both in 2D and 3D in that there are big differences. In 3D, you remember there was possibility to have a magnetic dynamo, kinematic magnetic dynamo, where magnetic field is created out of nowhere just because of instability. But in 2D it is impossible because magnetic flux tube cannot be stretched, and magnetic dynamo works only because of magnetic flux tubes are stretched, so that cross section becomes smaller, so that flux density becomes bigger. Now, with vorticity, it works exactly the same way, that in 3D it evolves towards narrower and thinner vortex tube, and vorticity grows. In 2D, that is not happening. And we'll be studying this now for a while, and let us see what we can learn from that. So let me now also start whiteboard. Okay, and share screen. And yeah, the equation was something like that. We have a full Lagrangian derivative of vorticity omega, and then this well, first, before I write that, actually, we had it in a little different form, right? We had in such a form that the partial derivative d omega over dt equals something like curl of. Okay, I guess I need to start writing on my on my laptop, because I already ran into issues on my screen. Well, just a moment. First, I guess we need to stop it. Usually you had it worked for a while and then it stopped working, but today it stopped basically immediately.
Sorry, do you want a mouse?
No, the mouse is not an issue. I'm quite used to working with my dashboard, but let's see how it works. There's also another issue because it sometimes writes because I support my hand on my tablet, and then also some lines which are not supposed to be there appear, but at least it should be much better than what we have had thus far. Okay, so d omega over d is curl. No. Wait. Why it isn't working? Maybe battery has died. Oh, too bad. It's probably battery died. Oh well. I was so optimistic that now I can start working, but this appears that pencil needs to have battery. Okay. Then I still need to go the old way and just try to be very careful. Maybe omega it is now curl v cross omega. And then there was some diffusivity also because of viscosity, but that's what we are not so much focusing right now. We mainly work with this Taylor equation without the viscosity. And then I don't remember last time, did we move from this 3D equation to 2D? Probably not. So this thing here, this is in 3D, and this describes the fact that what is the flux is concerned. So this basically means that integral over a closed loop of omega and not closed loop, but closed surface, material surface, say omega dot dA, where that loop is drawn over a material loop, so that guy here is conserved. I think what is the flux is conserved. Now, but let us try to move from 3D to 2D. And so in that case, in 2D, what we have? In 2D, we have velocity is in XY plane, and depends on X and Y. And in that case, velocity, if we have incompressible fluid, then in that case, we can express V in terms of stream function. So in 3D, we have, because we have divergence of V is 0 for incompressible fluid. And then from here it follows that V is curl of vector potential A. But in 2D, vector potential, because it's V itself is in XY plane. So curl, and then we can take A always parallel to the Z-axis and say that A is Z unit vector and what we call stream function of X and Y. And in that case, it basically also becomes a scalar quantity similarly to scalar potential what you have when gradient of something is there. And now let us plug this A into the equation we have. So this goes into B together with the corresponding A goes to first equation. So this needs to go to here. But first, let us change. Let us calculate B as a curl of A. So in that case, this B as a curl of A becomes curl of Z unit vector multiplied by psi, which is a function of X and Y. I'm not going to write it now always. And because Z is a constant vector, so differentiation doesn't apply to that. So nabla is applied only to psi. Nabla is applied only to psi, and so we can rewrite this as gradient of psi cross Z unit vector. So this is something which is always perpendicular to the gradient, which means that it moves along the isolines. So if we take V because V is perpendicular to gradient of psi, so V draws isolines, so psi xy constant represent streamlines. Streamlines of the flow. And that's also why we call it stream function. And now let us plug in this into the original equation, and in that case, let us see what we will have. So first we need to calculate omega. Omega, which is curl of psi, curl of phi. And this, if we plug in now V as this expression here, gradient of phi cross Z, then this becomes curl of cross product psi cross Z. And this equals now we apply the vector product, the double vector product rule. So that would be Z gradient of psi vector and the dot product of gradient and Z, but that is 0. So that would be, let me still write it at the beginning. So that would be another order. Z unit vector dot nabla derivative in the direction of of Z axis and of gradient of psi and minus now Z vector and the dot product of the other two, but the dot product of other two now becomes nabla square of psi, or Laplacian of psi. Now, because this guy here is 0, because we assume nothing depends in that direction, but this derivative along that direction, so this becomes finally equal to minus Laplacian of psi. And that's what goes into the first equation. Omega is Laplacian of psi. And so let us rewrite it. D Laplacian of psi over dt equals nabla cross. Now let us keep it here v, then let's not substitute here v, and then there was v cross omega, but cross is the z unit vector and Laplacian of psi equation like that. And now let us expand this double vector product. This becomes now v first v and dot product of nabla and yeah, but first that here we have two variables, actually, two functions, v and psi. So nabla actually applies to both of them. So let us, because of that, we have actually four terms here once we expand it. So this becomes now first when nabla is applied to v. First when it applies to v, and then first term is nabla dot v, but this is divergence of v, right? And multiplied by z and Laplacian of psi. And then we have minus and then we have dot product between nabla and z unit vector, nabla dot z unit vector, and z nabla is applied to v and not to Laplacian of psi. So v and but either even if it's applied to which way it's applied, either to v or to Laplacian of psi, it is 0 because it is the dot product of nabla and z, so it's basically derivative in the z direction. So this gives us anyway 0. So this is 0. And this is also 0. Because divergence of v is 0. And now we have only one term left, and that is when we have nabla and nabla dot v applied to Laplacian of psi. So it comes with minus sign because we have dot product between nabla and v, So we have here V nabla and Laplacian of psi and a unit vector of Z. Now, is it more or less clear what I did here? So it depends how good you are on vector calculus. Toma, how are you? Did you manage to follow what I did here?
Yep, pretty clear. Thank you.
Guys here, Otto, we did quite a lot of exercises, and now I have something in the style of that. So yeah, Spanish guys probably not that good for you, or it depends how much, but probably not. Okay, don't worry. What is also important here is result. If you manage to follow, everything was fine. But if not, then the result matters. Tudor, what about you? Thinking.
I don't fully get it.
Okay. We can go through it once again, but before I do that, let me write it just the result. Let me write the result. And now if I bring that guy to the left-hand side, then we have what? Then we have d over dt plus v nabla dot nabla. And everything here is applied to Laplacian of psi. And now the Z unit vector doesn't matter because, well, this happens in Z direction. We can just drop it. So what we have at left-hand side is so-called Lagrangian of material derivative, or full derivative. I think we mentioned it last time. And it's often written as in this form. And what does it mean? It means that this Laplacian of psi of vorticity moves along with the material particles together with the fluid. So Lagrangian derivative in a co-moving frame is zero, so Laplacian of psi is conserved in 2D. So that was kind of to be expected. Because, as we discussed before, similar to magnetic flux, vorticity flux is conserved for vorticity tubes, and if vorticity tubes cannot stretch, then due to compressibility, the cross-sectional area is constant, and so it means also the vorticity flux density, which is the vorticity itself, is conserved. So actually, you can understand it in that way as well. Yeah, now actually what we really did not do, but I think in one of the lecture recordings it is, just to motivate that the 3D equation, what we had at first, indeed describes the conservation of flux in Lagrangian loops. That's what we argued that based on what we know from electrodynamics and electromagnetic analogy, we derived equation for magnetic field, and it is exactly the same shape with the equation for V. And for magnetic field, we know that there is Faraday law, and if we ideally conducting fluid, then electromotive force must be zero, because otherwise you would have infinite currents. And so I deduced that there must be magnetic flux conserved, and that's why that equation must describe the fact that magnetic flux is conserved. It would be still nice to derive it from the first principles, like from geometry, and that's in one of the lecture recordings it is in there. You can what you basically need to do is you draw a material loop and then follow how it moves. So if it's like just a sketch of the proof. sketch of the group. Let me type it. You see, it's safer because if I start to write, then again some error might pop out. How to prove that the 3D equal on the previous page describes the fact that magnetic flux that the flux of vorticity is conserved through material loops. And the sketch goes like that. So you take material loop. And then it is transported somehow with the fluid. At next moment, it becomes something like that. And then there are here and there differences in the area which is occupied. So here is where things happen. From one place it moves away and it moves into the other, and just you need to calculate the flux change through these paths here. Express them and then integrate and apply Stokes theorem, I guess, and then you obtain the result. Something like that. Okay. So that this is that's a sketch. Yeah, but we dropped that part, and now we honestly arrive for 2D version without any shortcuts. That full derivative of vorticity, which is Laplacian of psi, is 0. And now, yeah, I promised to have just a repeat. So look at things what I hear and how we got it. So we have this thing at hand. And now we need to simplify it. That number here is applied to both phi and psi. Now what we need to do is expand double cross product as, let me write it here formula as well, A cross B cross C is B A dot C minus C A dot B. If you want, I can write here also vector sign on those. All right, so we apply this formula. And then we need to follow to which terms nabla is applied. Due to the product rule for the taking product of two functions, so nabla needs to be applied to both of them. So we have here from vector calculus, we have two terms, but it becomes now each of them becomes in split into two. In first case, nabla is applied to B, and in other case, nabla is applied to psi. Now, first, this term here, so we have a z Laplacian of psi. So this is now now that term here, that BAC term here, because that unit vector is in the role of C vector here. And now first, when nabla is applied to B, So this becomes divergence of V, which is 0. We have this same term later as well, and that's here. So this is also the same term, but the difference being that in one case, I think actually that is one mistake, by the way. That is one mistake, by the way. So this term here, first term should have minus sign. Because we have minus here, right? And then this term here should have plus sign because that is that term, not that term, but that is that term over there, which comes with plus sign. And so that is with plus goes. And here I just was lazy, actually that nabla is supposed to be applied both to V and to psi, but because it's derivative in that direction, in both cases it gives 0. We just wrote it because I've added once. And now the final term, it's the same as first, but nabla is applied to Laplacian of psi. We just arranged the order of nabla and V so that it's clear to where nabla is applied. So if I had it this way, then nabla is clearly applied to V. It would have been even clearer if I had wrote that the Laplacian of psi to left-hand side to it. But nabla is applied to V, and the second case, nabla is applied to psi. I write just first the order of the dot product, so that it is clear that nabla is not applied to V, but is applied to what is right-hand side. Now, Dodor, is it now okay? Okay. And Otto, maybe also you record a little and make what I did back then. All right, so now we have that is important result for 2D. Now, what does it mean? It means that actually we have infinite number of conservation laws. Because now if we suppose we have a tank with water or something which is carrying it, and we have here a certain small piece of fluid which evolves into later on into somewhere else, something with equal area, because it is incompressible, and it carries the same value of vorticity. So the same Laplacian of psi, what we had here, the same Laplacian of phi, that is constant. Laplacian of psi is omega, yeah. So that Laplacian of psi is constant. Now, if we integrate over the entire volume, so if Laplacian of psi is constant, just for brevity, let us use omega equals Laplacian of psi. And so if omega is constant, then any function of omega is also constant. For instance, omega to the power of n, where n is a certain number, is constant. And now, if we integrate over the whole volume what we have at hand, so fluid volumes just displace from one point to the other point. But all the areas are preserved and all the vorticity values are preserved. So because of that, we have integral of any function of omega over the whole volume of space, which is two-dimensional here, that is constant. And now, because it is any function, so we have infinite number of conservation laws. So this is a conservation law, right? In particular, important is omega square. So this is entropy omega square. The square R is constant. So this we discuss later when we speak about the inverse turbulent cascade. So this is important later. For the time being, we study a little different things. So in turbulence, what is important is, as said, a mixing of vorticity, because as I discussed last time, vorticity is born on the surfaces, on the walls of the vessel, because inside, if vorticity was zero, it remains zero. So it is born at the walls, and we need to know how it is mixed. Now, another thing which is quite, you can see here and there are vortices. So what is vortex? Two-dimensional vortex can be, you have, the simplest case is cylindrical vortex. So here we have, let us say, a region where we have omega equals constant. And here outside, omega is zero. Okay. Now, we would like to know now how the velocity field looks like. On the one hand, on the other hand, we would like to know if this vortex is stable or not. Meaning that if we perturb a little the shape of the sphere, it will remain. Will it remain more or less still circular, or maybe the perturbation grows and it will become something completely different? That's what we are doing. So first, what is the velocity field? Is such a vortex stable? Now, first question, does any of you have answer how the velocity field looks like here? No idea? Or maybe you have some idea. Toma, what about you? Do you know?
Sorry, I was writing down. Could you repeat the question?
The question is, if we have a situation like drawn here on the screen, that we have in a circular region, we have omega constant vorticity. Outside of it, omega is zero. So this is a cylindrical vortex. The question is, what is the velocity field here?
If we were to try, I would try to essentially take the circulation of velocity on a...
Very good. So as Otto suggested, we need to take vorticity, we apply Stokes integral theorem and calculate vorticity along a closed loop. Now we have different situations. First, our loop goes outside, and the other it goes inside. Now, and if that radius here is R capital, so let the radius be R small, and we consider different cases when R small is larger than R capital and the other way around. Now, first, R is smaller than R capital. Now, according to Stokes integral theorem, we have 2 pi R times V. Okay, first, before I do, let us rewrite here V as curl of omega. now, because of that, if we take now from left hand side and right hand side, if we integrate this over a closed contour, dl. Then left hand side becomes circulation and right hand side becomes integral over surface drawn on that loop. So B dl equals integral omega dA. Yeah, and now let us finish this. So we have a 2 pi RB is the left hand side of this equation, and right hand side is pi r square multiplied by a, multiplied by omega. So that equals pi r square omega divide, pi cancels away. R square omega divided by 2 and r small. Like that. And this is when r small is larger than r capital. Second, when r small is smaller than r capital, then it becomes modified. So that right hand side has also r small, 2 pi r v equals pi r square omega, so that v equals omega r divided by 2. Okay. So what does it mean? It means that the interior rotates as if being a solid body at angular speed of omega over 2, right? Do you agree? So interior of such vortex rotates as a solid body. And that's pretty much what happens at the centers of the hurricanes. So there is so-called eye, where very weak winds are, and there this just rotates in a solid body because it's that's where the vorticity lives. Outside the air is more spiraling in, bringing more or less vortex-free flow, and vorticity is at the center. Now, everything clear, everyone? Yeah.
I have a naive question and perhaps a more interesting one. The naive one is, if V is nabla cross omega, then why do we have V where omega equals 0?
Once again?
If V is is curl of omega,
Yeah.
then why do we have non-zero v in the portion where omega is 0?
Oh, my bad. Omega is curl of v other way around, of course. Thanks for drawing my attention. So I see theorem is don't write like I was in a semi-automatic regime doing things. I was in a semi-automatic regime writing. Yeah, let us fix. Let us. I kind of invented something. It's a little strange, but just went on and yeah, of course. So omega, what is it? Is curl of v, right? And then now we apply Stokes theorem and we integrate now we integrate this by dA. Okay, and now we apply Stokes theorem. Okay, after integration, left hand side becomes omega dA, right hand side becomes integral of curl of v over dA, which according to Stokes theorem is v dl. Now it's fine. And thanks for pointing out.
The other question is, what would be the electromagnetic equivalent of the equation?
Vector potential A is electromagnetic equivalent, and in 2D it's also you can work with stream function. Stream function is in that case the line where the current flows, lines of constant current. Here,
So this is a wire.
Yeah.
So this is some weird wire that is fully carrying current on its entire surface.
Yeah, if you had this thing in here in magnetohydrodynamics, it would be everything depends only on XY plane. Magnetic field is parallel to z-axis, and curl of B current is also in XY plane. And if we introduce now stream function, then magnetic field lines are lines of curl of B, which is a current density. Curl of B, which is a current density, becomes lines of constant stream function. Okay. Any other questions? Everything clear? Fine. Now that was the answer to the first question. What is the velocity field? Second question: is such a vortex stable? And now that's a quite a bit more difficult question, is it? Stability analysis is well, depending. It might not so easy. Sometimes it's just a tedious work, a lot of math. But here we try doing now a small trick, and before that we need to go a little into a general question of how we can show that something is stable. And what ways of showing that something is stable do you know? Yeah, Tudor, saying you don't know anything. You know some. Okay, please tell. What is?
I don't know.
How to show that something is stable? I guess Micah and Otto either don't know, and I doubt.
Something about the energy of the system. Something about the energy of the system.
All right. Yeah. Okay. Tudor went ahead and said that something to do with energy of the system. Now, how does it sound? Otto, do you think it's doable? Something with energy. How and exactly then what? Toma, what about you?
How to show if it's stable?
Yeah. Unstable. Stable, unstable. How to show?
Cool. I know it's possible here in a 2D case. 3D, it's more complex.
But in 3D, it's actually in 3D, it's probably it's not even stationary. Here, actually, you saw that it is stationary. How did you know that actually, by the way, it is stationary now? This vortex.
Experience.
No, not by the experience. Just remember the equation what we had. Equation of equation stated now that omega is transported with the fluid. For Lagrange derivative is 0. So since our streamlines do not cross the border of vorticity and no vorticity, so all the particles either circle in the region where there is omega or where there is no. And everything is fine. Our equation is satisfied for this flow. Okay, so it's clear that it is stable. No, it is stationary. Now in 3D, it might even not stationary. You can consider, what you can do is consider this two-dimensional flow and study three-dimensional stability. And that is, as Thomas said, it is definitely also stationary because it is still the same flow, but now we consider it three-dimensionally. So you understand what I'm speaking about. So we can study either two-dimensional stability, that's saying that it still is forced to remain two-dimensional, but we want to know if its shape is stable. The other possibility to say that, okay, it is two-dimensional, but it might not remain two-dimensional as a flow later on. And let us study if it is stable with respect to three-dimensional perturbations. And that would be much more difficult. But let us do only the first studying two-dimensional stability.
Quick question. Do hurricanes obey this two-dimensional approximation mainly because they're much wider than they are tall?
I think, please repeat your question.
You use the example of hurricanes. Do they more or less obey this two-dimensional approximation of, solid body rotation in the middle because they're so much wider than they are thick or tall?
Yeah. So exactly, because atmospheric turbulence in large scales, it is 2D. Exactly because it is so thin as compared to dimensions. In horizontal direction, well, it's something like 10 to 20 kilometers thickness. Well, the different layers move with different speed, but we can just consider one single layer then. And as compared to thousands of kilometers, or well, on the order of thousands of, at least many several hundreds kilometers, it's much smaller. And it is works out as essentially two-dimensional. The same applies to oceanic flows, in large-scale flows. Yeah, here and there you need to take into account, but as you will learn later on, so cyclones and anticyclones develop exactly because it is two-dimensional. Otherwise, they would not develop. Did I answer your question?
Yes, thank you very much.
Okay, and now to the question how to show if it is stable or not. So there was idea about energy. So Tudor, maybe you elaborate. What is your plan?
Don't really know how to define the energy of the system, but if I showed this is a minimum or a maximum, then perhaps a perturbation would solve itself, or it would at least oscillate within a bound.
Yeah, very good. So in mechanics, you know that system is stable when potential energy has minimum, right? So, but what is so special about being minimal? Why not maximum?
You're walled off. You're walled off. You can't go any further. Or it is difficult to climb. It's not easy to fall. Sorry, it's very easy to fall. It's not easy to climb.
But
Or rather, you can
mathematical.
turn it into kinetic energy, but there's nothing to turn
right.
into kinetic.
Yeah, exactly. The reason is in kinetic energy, because kinetic energy has always minimum. And the thing is not about potential energy having minimum, but the thing is about full energy as a function of phase-space coordinates, coordinate and momentum. Or well, if you take in Lagrangian then coordinate, then there's a derivative of coordinate. So it needs to be minimal in phase space. And kinetic energy has minimum, so we cannot have maximum. Our extremum can be only minimum. And that's why our potential energy has to be minimal. But actually, this stability criterion can be generalized. And in such a way that a system is stable. Let me write it down. The system is stable when there is extremum of one of the conserved quantities. A conditional extremum on the fixed all the other conserved quantities. So okay, now just to get for you to get the idea about it. So some of you might have seen experiment about stability of rigid body rotation. Now, let me try to fast Google if I can find if I can find a video. Made in International Space Station. Rigid station. Yes. I used to have that link somewhere, but then maybe this one. Yeah. I think I need to share the screen. Okay, now you know why you can use International Space Station. And so you never had this shown in someone?
I wasn't able to hear the volume. Is that normal or?
Sorry, go ahead.
I wasn't able to hear the volume of the video. Was that
Oh,
normal?
you didn't see the video? Oh.
Oh, no. I could see the video. I just couldn't hear anything.
Oh. I think this text was not that important. What you saw was that if you take a rigid body and rotate it so that rotation is axis provides either the largest or smallest moment of inertia, then it is stable. If you take an axis which corresponds to an intermediate value of moment of inertia, then it is unstable. That is a third.
Okay, thank you.
So you can just play again to see. So I can comment now. I can just mute it and just comment. Yeah. So now if we put rotating that way, moment of inertia is maximal, right? All the points of the rigid body are as far as possible from the rotation axis, and it is stable. Now it is minimal because you keep as close as possible all the points of the rotation axis. And now it takes intermediate value. Now what he puts into rotation. Okay, and as you see, it moves away from direct rotation very fast. So this is unstable rotation. Okay. Is that clear?
Yep, thank you.
Okay, and now going back to OpenBOD, what this has to do with what we have been talking about. Now, for rigid body rotation, which kind of conservation laws do we have? Anyone?
Energy?
Energy, yes. And for that?
Everything.
Momentum?
Inertia.
What?
Just everything.
Everything is conserved. Mass is conserved. Not interesting. Okay, what else?
Angular momentum?
Angular momentum, yes. Angular momentum. Okay, let us write it down. And now L is a vector. And now we need to express energy. And energy can be expressed in terms of angular momentum and moment of inertia as follows. Kinetic energy T is L squared divided by 2 and a moment of inertia, is it? Do you agree? Does everyone agree with this? Tudor is making, now Tudor agreed. What about the rest of you? Okay, just to be helpful, L equals I times omega. Full energy, it certainly knows that it is I omega squared divided by 2. And if you plug in, then I obtain this. And now L is conserved, and I wonder if energy has this conditional extremum. And indeed, if I takes the smallest value, then T has maximum. If I equals to I maximal, then E as minimum. Agreed? There you have it. Total stable. Well, it doesn't now say anything about the non-extremal case. And in general, you cannot say about stability in those cases. But here probably you can deduce that it is unstable. Anyway, in most cases, what can be unstable, it becomes unstable. And in those two cases, thus it cannot be unstable. Because of conservation laws. Strictly speaking, to show instability, you need to do perturbation analysis. Yeah. So is it clear to everyone now? How this conditional extremum works out? Now, regarding vortex. So what we are trying to now convince ourselves is that the vortex has also conditional extremum of something. So what do you think of what it can have extremum? And conditional extremum.
So to have an extremum, something has to be constant. So would it be the integral of omega?
Yeah, so conditional extremum by fixed vorticity, that's what we're going to consider. So total vorticity, basically because any power of omega is constant. Well, another way, what I can say is that the valid perturbation with respect to which we need to consider if it's minimal or maximal are the perturbation where d omega over dt, Lagrange derivative of omega is zero. So we can displace region with omega to somewhere and regions without omega to somewhere while preserving total volume. And that's all we can do. We cannot mix it, we cannot move it discontinuously to somewhere like we take omega in between the vortex and move it far away, that we cannot do. We can move only so that it can be continuously displaced, those parcels with omega to somewhere. And then we need to show that kinetic energy is either minimal or maximal. Easy, right? Now, the question is, how do we calculate the energy here? And so what is what is energy here at all? So, so we have here vorticity. And we ask what is energy? And energy is kinetic energy, right? There is no other kind of energy, right?
Yeah, but how is this an extremum? Because if I make the circle smaller,
yeah,
increasing omega.
But you cannot make it, you need to preserve volume.
I need to preserve volume.
Yeah. So you cannot increase volume of the region with omega.
I see, I cannot increase omega to decrease the volume.
Yeah, no.
That's not.
You can only consider perturbation where Lagrange derivative of omega is zero.
Okay.
And now kinetic energy overall. By the way, how do we know that this actually is preserved?
Kinetic energy or what?
Yeah, kinetic energy. How do we know? Two-dimensional flow. Oh, well, actually three-dimensional as well, but we have equation D, original, in the original form, let us take rho dV over dt plus V nabla V plus gradient of P is 0. How to show that energy is conserved?
Where else would it go?
Ah.
Where else would it go? Where else would it go?
Where else
Would the energy go?
Who knows, but we need to obtain it mathematically from the equation. You have mathematical background, you need to be more strict here.
I mean, physically speaking, if there's no external forces, right, then the potential energy is going to be constant, and therefore the kinetic energy has to be constant as well.
Yeah, that's all fine, but it would be reassuring to have it from the mathematical, just from coming out from math, isn't it? For us as physicists, it's fine. Maybe we can keep it kind of like homework, maybe, to figure out if energy is conserved. And what you basically would need to do is multiply this by V, dot product, and then work out integrate over the space this square R, and then show that basically you need to arrive at the condition. You need to have several steps to show that d over dt of integral rho v square d square r is 0. That's what we want to show, right? If we take here multiply by v and integrate by d square r, then actually the first term, this is what will give us this guy here. All the rest needs to go away upon taking derivative. So we might assume something like non-moving walls at the and no flux, no fluid flux through the walls or something like that. We need to make some assumption to apply integral theorems for the total volume, so that we have here some derivatives. Say so need to go away upon applying integral theorems. That's it. That's the idea. Okay, let us not do it right now. You can consider it as a home exercise. Anyway, let us go on to calculate some kinetic energy. Now we have, what is here kinetic energy then? D. For unit density, we have integral 1/2 v square d square r. How do we calculate this? Yeah, well, for the initial situation, that's fine. But once we perturb it, we need to be able to calculate this guy even after perturbation. For this initial symmetric case, it's no problem to calculate because we already expressed V. But now we perturb the boundary, and then it is no longer that easy, is it?
Can we do some superposition principle or?
Superposition principle for velocity, yes, why not? You can calculate new flow field after perturbation using superposition, like plus initial.
And then apply some funny inequalities.
But let us do it another way. Now, let us use electromagnetic analogy. And so our equation for defining V is as follows. We have V is a curl of by V by V square. Let me write that way. V square is nabla psi square. Because well, it is rotated by 90 degrees, but we care about modulus, so let us not care about rotation. This on the other hand, that's what we want to calculate, the integral V square. On the other hand, our equation for relating V to psi is that instead of V, we calculate psi, but we are given omega. So our equation is omega equals minus Laplacian of psi, is it? So we are given omega, and we want to know psi. Because if we know psi, you know also V. Does this task remind you something? Omega is minus Laplacian of psi.
I mean, we already showed it earlier.
Sorry?
We already showed that it's a constant earlier.
Constant?
Laplacian of psi, yeah.
Yeah. There should be some non-trivial solution. Basically, you know it for unperturbed state, but I would like to know the general rule how to do it. And so my suggestion was to recall electrostatics. If I tell you a keyword of electrostatics, then does this equation omega is minus Laplacian of psi sound familiar? Yeah, Todor wants to say something.
Yes, it does, but
so
it's a long way to figuring it out.
Let us write it here down. Rho. No, wait, doesn't write it. Probably there is something. Yeah.
To me, this leads me straight back to superposition.
Now, if we recall this thing here, that rho rho divided by epsilon naught is minus its Laplacian of phi. Is this familiar?
Yeah.
It is. For finding electrostatic potential, right? Then what's next is how to calculate from here the phi based on rho.
Yeah.
We have green function. So anyone familiar with green function? Otto and Maike, do you have a equation of mathematical physics? You had already? Did Jan Janna tell you about the green function? So did you learn it properly? What was it? Toma, what about you? Green function.
Yes, but it's been many years.
All right. Okay, so maybe I'll write it down. So green function. This is solution of equation Laplacian of Okay, in terms of electric field, Laplacian of phi is Dirac delta of coordinate. Okay, and green function is solution of that. In 2D, it would be phi equals. Now you know what is two-dimensional potential, right? Logarithm. Two-dimensional potential is a logarithm of, and I think there is also 2 pi somewhere, 1 divided by 2 pi. Logarithm of r divided by 2 pi, something like that. Probably. And then based on that, we can write a solution. Based on that, we can write solution. Phi is integral of basically over all the point charges, rho at r multiplied by green function r prime. Yeah, so this is phi at r. Logarithm at of r minus r prime d square r prime, like that. Basically, that you knew actually already from electrodynamics, electrostatics, that you can just sum by superposition all the potentials of all the charges, and green function is just a solution for a point charge. Actually, green function is a very simple thing. Maybe you didn't understand it in the case of equation of mathematical physics, but actually green function is simple thing. Yeah, Tudor?
So then a deformation would be some sort of dipole, or
Deformation would be some sort of
dipole, or
yeah, perturbation is a kind of dipole, yes. Now the next thing is that how to obtain energy of the system. So now we learned how to obtain the solution, but how to obtain energy. What about that? So here again, what helps is the electrostatic analogy. Let me take a new page. Well, if we have energy of a system of electrical charges, now that how we write it, U maybe equals, or maybe W. On the one hand, it is integral of E square divided by 2 epsilon naught. The square of it depending if you're speaking about 2D or 3D, but we have here 2D, let us write it in 2D form. This on the one hand side. On the other hand side, it is also integral over all the charges, 1/2 of antipolar potentials. D phi r rho r Okay, now we have it again. I think my stop writing, I guess. Oh no, that's not that bad as well. So of R and the R D square charge. So this is DQ. That's the position of R. Okay. Two ways of calculating energy. One is interpreting it as electric field, and the other is integrating as charge multiplied by potential YTs and summing over all the charges, and factor 1/2 because actually in that way you count each of pair of interacting charges twice, so you need to divide it by 2. Is that okay to you? Now this can be shown, this equivalence can be also shown using integral theorems. So this can be another exercise to show mathematically. So this is what you know from electrostatics, but you can do it also mathematically. And if you like mathematical exercise, here you have it to show that those two things are always equal. Okay, and now when I go down to our what is the problem? Then T. Now we have T as. Now, what again? Omega was density, charge density, and the potential was the stream function. So we have equivalently, we can write it like 1/2 integral omega at r psi at r and t square r. And that's our energy. And now it's already, as you can see, this is something quite easily to calculate even after perturbation, is it? So that if we, now let us try to figure out what happens. We have here vortex. Initially, it is here omega here. Now we consider perturbation, and what the perturbation can be is that we take from somewhere, we take away this and move it to somewhere else. That's the only kind of perturbation we can make here. While we have that our constraint that our motion need to preserve vorticity everywhere. That's the only allowed perturbation. And now, as Todor said, we have actually dipole, basically. Perturbation is a form of dipole. But let us calculate now the change of the energy here. So we take well, now we need to keep in mind what was the potential actually before. So our potential pi was logarithm outside divided by. Maybe it's even not that important what its specific form. The thing is that psi is a decreasing monotonous decreasing function. So if we take here we take psi, then we have probably something quadratically growing here, and then oh no, sorry, not that way. It goes something like that. Something like that. But parabolic part and then logarithmic or slower growth. Logarithmic. And here is minus r squared. Minus parabolic part. Anyway, it is decreasing function, right? And so you basically move a charge from higher potential to lower potential, which means that you always decrease the overall energy. Okay, is that more or less convincing? Yeah, Todor has something to say.
Yeah, it's something quite interesting. I was thinking of the effects of moving the charge on the potential over the rest of the charges.
Yeah, very good.
But that's by the argument before is identical.
Yeah, right.
The potential the other charges had upon it.
Yeah, okay.
So you don't need to worry about the ugly integral.
Right. Okay, so there you have it. So it is stable. How is it? No, everything fine?
Yep, all good on my end. Thank you.
Now, how much time do we have? 20 minutes or so. Since we are right now at the instabilities, so regarding two-dimensional vortices, I think that's more or less what we discussed for the time being. But then later on, if we go to and this will be very soon when I go to Kolmogorov turbulence, then we return back here. But right now, still a little about instabilities. As mentioned, instabilities are important in creating turbulence, and one case is that Kolmogorov turbulence, when instabilities are born basically because of Kelvin-Helmholtz instability, and the other is actually what is quite important instability is Rayleigh-Taylor instability. So maybe we can spend this time here right now to try to derive Rayleigh-Taylor instability, which is actually quite important in the case of fluid turbulence. So anyone knows what is Rayleigh-Taylor instability? Tomo, what about you? Rayleigh-Taylor instability.
I've heard of it, but I forget what it is. Thank you.
Okay, then it was discussing. So once again, any turbulence usually starts from instability. And so Rayleigh-Taylor. Oh, crashed. Now OpenBOD crashed. Rayleigh-Taylor instability is instability of heavy liquid on top of light liquid. And so we have here on row 1, here we have row 2, and now we ask what is the is it stable? And if not, then how fast it will evolve. And now we use another way to approach stability analysis, and that is by introducing linear perturbations. And because it is linear, then superposition applies to infinitely small perturbation. Means that we can always linearize our equations even if they are nonlinear. So we take infinitesimal small perturbation and linearize. That's what we do always in such cases. And yeah, because it is we linearize it, we have linear set of equations, which means that superposition principle holds. And we can take, because of that, we can just, without any restriction of generality, you can take just a Fourier component and assume that this is sinusoidal perturbation. So we have here sinus kx. A height is amplitude. That is h cosine.
I can't see anything, sorry.
Oh, sorry. Yeah, I forgot to share. Thanks for reminding. I forgot to share. After crash. Okay. And now we use Lagrangian approach. So we need to first express kinetic and potential energy in terms of our variable. Our canonic variable will be h and h period. So raise your hand if you have had analytical mechanics course. Otto and Mike did have, I know. Spanish guys, did you have analytical mechanics? Do you know what is Lagrangian?
Yes, I think.
Okay, that comes from, if you know, that's good. You don't know? Okay. All right. Toma? Yeah, Toma has a question?
Oh, no, I was just saying I have had analytical mechanics.
Okay, you had analytical mechanics?
Yes, I have.
Okay, good. And now, it means that we'll be writing down kinetic energy, potential energy, and based on that, we can directly write down an equation of motion. Now what about kinetic potential energy? Let's start with potential energy, that's kind of easier. So we have here reference line, and we have as if some water elevated from another part, which is below the reference level. Reference level should be symmetric. Maybe I can just move it here, this line, I guess. Okay, looks better. Do you believe me if I write here now, but for potential energy, V is it is two-dimensional figure, so let us just consider per unit length in that direction. So V is rho 2 minus rho 1. Maybe rho 1 minus rho 2, let us write that way. So if rho 1 is bigger than rho 2, then initial potential energy is smaller. And potential energy will then increase. Still rho 2 minus rho 1. And then H, Z. Okay, so we need to multiply the height of center of mass with the displacement. Center of mass is at height Z over 2. And the mass is Z times dx and multiplied by rho. Yeah, okay, if I write that way, then actually I removed those things here before. And then I write here integral. So this gives us a potential energy of a column. Okay, let me draw here also what we are calculating right now. So we are calculating a potential energy of this column relative to the center reference level 0. Now, yeah, actually, we need to put here the difference of the densities because if we have column of rho 1 here, rho 2, column of rho 2 is removed. So rho 2 comes with minus sign, right? Having plus density of rho 1 in this black column here, meaning actually having negative density of rho 2 as compared to reference state when everything was plain. So do you buy this integral? Potential energy.
So is this just densities under gravity or what's the?
Yeah, G. Let us write G as well.
And this is just the green part. And this is just the green part.
But integrate everything so it can go also to the blue part. It is still positive because we have central mass is negative. The height is also negative. So it's yeah.
Right. The height is negative, but we're squaring it.
So okay, regarding sign here in blue part, you push down rho 2 displaces rho 1. But rho 1 is larger, so you still have positive energy.
Right.
Okay, so this becomes now just integral of cosine kx. Now over long volume, so oscillating part doesn't matter, only average value matters. And so this becomes G H squared divided by 4 because average value of those lines squared is 1/2 multiplied by rho 1 minus rho 2 and multiplied by but by integration we have still 1 divided by k, I guess, here. No, 1/2. No, okay, it's just the length of the vessel. We have very long L, very long length it develops. Okay. Now, if we want to add here also potential energy of the surface energy due to capillary effects, We could do that as well. In that case, we would need to calculate the change of total length of the for the surface. But looking at the clock, maybe this can be also as your additional exercise. To add into here the contribution of surface tension. Or maybe it's not that difficult. Let us see. If we have this is V1, V2 is a sigma integral and change of the length. Change of the length is change of cosine alpha, 1 divided by cosine alpha. So it is dx and a change of 1 divided by cosine alpha, where alpha is a slope. Is it right? Is it right? Dx is the length of the element, but length or horizontal length. In order to have the length of the fluid surface, we need to divide by cosine of alpha, but we need to compare the change. So this is actually cosine alpha minus 1 divided by cosine alpha minus 1. Let me write it properly then. Let me write it that way.
I mean, it would have gone outside the integral as a delta.
Doesn't matter everything which is in row it will multiply by dx and so on. So in maths you sometimes write dx also at the beginning, not always.
But yeah.
Cosine alpha minus 1, like that. Do you agree now?
Yeah.
Okay, and now this becomes, because alpha is very infinitely small, so this becomes a sigma and alpha square over 2. Integral alpha square over 2 dx. But this alpha square is actually tangent alpha or derivative. So this is a derivative of that guy here. So it is alpha is k h cosine kx. Okay, we have alpha square, so it is like that. Like that. So it becomes a sigma k square divided by 4 and h square and L, like that. So we have also potential energy of the surface tension as well now. Everything fine? And now kinetic energy. And kinetic energy is a little more tricky to calculate.
Sorry,
Yeah.
I'm not really understanding where, so V1 is the potential energy in the little black column you drew, correct?
Yes.
And then what is V2?
V2 is potential energy due to the change of surface energy. Because if you have wave, the surface is bigger and surface energy is also bigger. And so we calculated it. So if dx is a horizontal length, then the surface element length is dx divided by cosine alpha. And we calculate the change in the surface element length. So compared to before the wave and after the wave. Before the wave, dl was dx. After the wave, dl is dx divided by cosine alpha. So the change of the length of the segment dx is what we have in the integral dx times 1 divided by cosine alpha minus 1. And now we approximate cosine alpha as 1 minus alpha squared divided by 2. Then it becomes sigma alpha squared divided by 2 dx. And then we keep in mind that the amplitude was very small, so the slope angle is also very small. We substitute alpha as a tangent alpha. And then we have that relationship alpha square is k square h square cosine square. Is that fine?
Yes, that makes sense. Thank you.
Okay. And now kinetic energy, T. And T is a little more tricky. Maybe we need a new screen, but okay, we can try right here, but I'm not sure if we can manage to do it. T starts from noticing that we had no vorticity. And so we had omega 0. Omega is 0. So curl of V is 0. And now if we take here from this equation now another curl, and then we obtain Laplacian. From here, Laplacian of V is also 0. And or maybe it would have been better. Okay, anyway, we could also work with the, never mind. It would be better with, because omega is 0, so Laplacian of psi is 0. And then we need to figure out what is psi. Psi is a stream function, and now we assume that it behaves in x direction as sinusoid. So psi equals certain psi as a function of y and e to the power of I k x. Okay? And now this must be, Laplacian of that must be 0. So it means that d square psi over dy square minus k square psi is 0. And from here we obtain that psi equals psi naught e to the power of plus minus k and y. Okay, that's what we have. And now the question is which sign should we take, plus or minus? So it's quite obvious that it to infinity. So we need to take here psi naught e minus k and y modulus. If y is 0 is the reference line. So it decays exponentially in both y with both up and down the velocity. Okay. And now we don't have that much time left. Maybe we can make a shortcut. Basically, what we now need to do, we need to integrate over the whole space. And that is not that difficult now anymore because we have expression for psi. And the expression of psi immediately gives us expression for V. And I hope you will believe me if I tell you that T will be something like that. H dot time derivative of H is the speed of the line, level line, and then squared, and then contribution from the top is rho 1. Probably here divided by 2 as well, or maybe in 4. 2 comes from the kinetic energy, another 2 probably from from the square, integrating square, I guess. Now, psi1 row 1 v square gives kinetic energy from the top, and row 2 gives from the bottom, and then we have thickness, because only the thickness of 1 divided by k moves. So actually, okay, this should be integral always in 2D plane. And now, integration by in x direction gives us L. Integration in y direction is integral of 1 divided by, okay, this will be something like that, e to the power of minus k y modulus. From minus infinity to plus infinity, it goes to 2 because with square the velocity, so it goes to minus 2ky and dy. And so this gives us prefactor of 1 divided by 2k. This integration, right? Both from 0 to infinity and from 0 to minus infinity. Let me fix here actually this I assume from 0 to infinity. And from 0 minus infinity to 0 gives the same thing. So if from 0 to infinity gives you row 2, and from minus infinity to 0 gives you row 1, which is both. So 1 divided by 2k as well. And now we have more or less a clip which I always wanted to have. So Lagrangian. Lagrangian equals now kinetic minus potential, so it is h dot square divided by 8k row 1 plus row 2l minus, now what was that again? Yeah, so it's V1 and V2. So we have H square L divided by 4, and H square L divided by 4, and then there was G, and there was G came with row 1 minus row 2. Row 1 minus row 2, which was it? Row 1 minus row 2 was the other way around. And plus sigma k square. Like that, let us check. Row 1 minus row 2 and sigma k square. I think it's fine now. That's how Lagrange is. We agree? Now, see all what we work for equation motion what comes from here. And so d over dt, full derivative of d over dt of dl over dh dot. Of dl over dh dot is h dot divided by 4k row 1 plus row 2 times L. Okay, and this equals to dl over dh, which is minus H over 4 over 2 L and G row 1 minus row 2 plus sigma K square. Okay. And this thing here, left hand side, is H double dot. And row 1 plus row 2 divided by 4K times L. And this is our equation of motion. This is left hand side. This is right hand side. And yeah, now what we have is a dispersion relationship. We can also say that H double dot is actually, this is minus omega square row 1 plus row 2 if we assume it is sinusoidal. And it is sinusoidal because you can also solve it using characteristic equation. And then we have, from here we have directly omega K relationship. Let us rewrite it. Now what cancels is L capital. And so we have omega square equals row 1 minus row 2 divided by row 1 plus row 2 multiplied by the adhesion factor 2. I think. No, 2 goes up, probably. 2 goes up. Times G. And this, and this already has Rayleigh-Taylor instability now, because you see, this omega square can be both positive and negative. If it is positive, then it is deep all the way. If it is negative, then it is instability. But let us write the other term as well. So minus sigma, and K, sorry, K is missing here. And sigma K cubed divided by and 2 factor of 2 divided by row 1 plus row 2. Something like that. So I hope everything is correct. There might have been one thing happening because we made a shortcut. We might have a factor of 2 wrong in the row 1 plus row 2 term. That needs to be checked. Because we did not write the math properly, we might have gone wrong over that. Because I feel maybe there is no factor 2 over that. It needs to be checked. Other than that, that's the result. So now, before we leave, let us have a look our fruit of our work. First thing is that we might want to make a plot how this omega square depends. Omega square depends, and before we are going to make a plot, assume that this first term is positive. If omega 1 is larger than row 2, 1 is larger than row 2, and then the first term is positive, the second term is negative. No, I again completely messed up. This should be plus. Because I had omega square is minus, so forgot that minus, and now to have was it row 1, row 2 is on top. So row 2 is on top. Yeah, now it's correct. Once again, so if row 1 is larger than row 2, it is always stable because the first term is positive, second term is positive, omega square is positive. So omega frequency is a real number. This is oscillations, this is stable. Now assume we have first term is negative, heavy liquid on top of light liquid. That's what is called a Rayleigh-Taylor instability case. And then we have, then it depends, the overall result is positive or negative depends on the value of K. And now let us make a plot for that case. Let us make a plot for that case, and at large K, a second term dominates. It's definitely at large K it is positive. So it will look something like that. Minus omega. Minus omega will look something like that as a function of K. Not minus omega, but minus omega squared. This goes like K cube and K. At large K, it is. Let's do it. Just to me, it's not to calculate. Let us put here plus. So here it goes like that, and then it goes maybe. So a small case, we have only dominating the second term, and so it is a linear function, so it goes through 0. So it should look something like that, I guess. Do you agree?
So it only has 2 roots.
Yeah, it has 2 roots omega. Now, plus or minus, as long as omega is positive, here are sinusoidal weights. Because the dependence is EI omega t, you don't care if it's plus or minus, it's the same goes anyways, right? As long as omega square is positive, you don't care if it's plus or minus. If, on the other hand, if omega square is negative, then we introduce gamma as I times omega, I gamma as omega. So if we plug omega as I gamma into here, then I square goes to minus. So then becomes E minus gamma T. And now we care about if it's plus or minus. And because we have 2 roots here, then it becomes now e to the power plus minus gamma T. And one of them is stable, and other of them is unstable. And that's what you usually have. Like if you have pencil falling from its tip, you solve it, you also have exponentially growing and exponentially vanishing solution. What you see at the end of the day is exponentially growing. And now the situation here is that we have a range when you have gammas, which are which correspond to instability, because we have positive gammas, gamma larger than 0, instability. Gamma, no, it's the other way around. Gamma larger than 0, because I defined as each was minus gamma t. So let's make it the other way around. Gamma is larger, smaller than 0. If gamma is smaller than 0, even though the lowest minus gamma t is exponentially growing function, t, so it's unstable. If we have gamma larger than 0, then it is stable. If we have both stable and unstable, then unstable, of course, wins. Because one solution vanishes, the other does not vanish. And as you know, the contributions from the two solutions in linear combination come from initial conditions. So you never have initial condition when the unstable part is completely 0. So always unstable wins. And furthermore, we have actually here not only two solutions for gamma, but keep in mind that we can have different sinusoids. We consider just one sinusoid for given k, the wave vector. But we can have different k's, and what wins now, if we consider all the k's, is the most unstable, the one which grows the fastest. So this is k star, which is the most unstable one. And the most unstable solution. Okay, so we are now more or less finished. So we obtained nice results. Actually, we have also a solution which covers both gravitational wave, both capillary waves, and the Rayleigh-Taylor instability. Three different phenomena. Our omega of k, which we obtained, covers three cases. Let me frame this important result as well. That's it here. So Rayleigh-Taylor stability, gravitational water waves, capillary waves. Three different phenomena covered here. But that was just one example how you do stability analysis. But the procedure is universal. Whenever you need to do stability analysis, it is always the same way. You make infinitely small perturbation and obtain evolution equation for the amplitude of that solution. And a nice example, actually, with which you can play at home is a Rayleigh plateau instability. A Rayleigh plateau instability, that is instability when you have a water cylinder breaks down into droplets. And in there, it is a little bit more difficult to calculate because it is a two-dimensional. It is cylinder. You need to go into solve a Laplace equation in cylindrical geometry, obtain Bessel function and things like that. But at the end of the day, you obtain quite a similar picture that you have certainly a wave vector along the water column, which is the most unstable, which wins. So you can play with your faucet water coming out and how if you make the water flow rate very small, it breaks into a droplet. Let me add one more page here. And so here water comes out and now it goes like that, and then it becomes unstable because cylindrical surface has a lot of surface energy. Droplets are much energetically more favorable, so it becomes first away. So okay, not too well drawn. So it goes something like that. So narrow, thicker, narrower, thicker, narrower, and then it becomes into droplets. And this is called Rayleigh plateau instability. That we are not going to calculate because in Bessel functions would take too much time from us. But it's nice physics nevertheless. And now one thing what we did not cover today was very important turbulence is Kelvin-Helmholtz. I'm not sure you need to do it. Let's see if we'll do it next time or not. It is also somewhere in lecture recordings. I'll revise how much time do we have and if we want to do it or not next time, Kelvin-Helmholtz. Okay, and that's complete for today. Any questions?
Yeah, quickly, could you go back to page 9, please? I missed something.
Which page? 9.
Page 9, yeah.
Okay.
Could you scroll down a little bit, please? It's at the very bottom of the page. I just missed.
Okay, just a moment.
Thank you.
Yeah, because psi is a product of function which depends on y and which depends on x. We can easily take Laplacian. It comes in 2 parts. Derivative around y is the first one. Second one is direction, derivative in x direction. That gives us minus k squared psi, the second derivative. And then this is equation for finding psi. And this we solve using a characteristic equation to find it to be exponential function e plus minus ky.
Yeah, thank you. I just missed that last equation.
Okay. Anything else?
All good for me.
Yes.
Where would the speed go in our drawing?
Speed in a drawing.
Yeah.
You mean how the water moves in wave? That's a good question. And it water parcels, by the way, move along circles. All the water parcels in wave move in circles. So it should be emphasized that this solution is for water waves in deep water, because I assume that water depth is infinite, right? It is basically it needs to be much larger than the wavelength, because we see that water partial speed goes down as exponentially with distance, and it is as wave vector of the wave. So if you go deeper than the wavelengths, your water parcels speed will be already very exponentially small deep in there. So this model works if your water is much deeper than the wavelengths. Oh, well, not much deeper, because we have k, which are all by actually wavelengths. Depth equal to wavelength is already very much a deep water wave. There is also shallow water wave. If you look here, we have dispersions at omega square. Let us go. Where was it? Our final result. If we look here, omega square is gk, which means that phase speed omega divided by k depends on k. Omega goes as square root of k if we neglect the capillary part. And then this, for deep water, you have a strong dispersion. Longer waves move faster. In shallow water, which is the other way around, water depth is much smaller than wavelengths, then phase speed is constant, and all the wave move with speeds equal to square root of gh, where h is water depth. Okay.
Follow-up question to this. Yes. If the particles or the field moves in a circle, how can we have curl V equals 0?
Curl 0. It is a circle in time, but not in space. Of course, curl is 0. But if you follow, sit on a water particle and see how it moves. It moves in time, it performs circle. Because it's sinusoidal in one way, it's sinusoidal in another way. Phase shift is pi/2, so it moves in circle. Okay? But any instantaneous moment, of course, streamlines are, of course, not circles. And because you have already solution for psi, streamlines are psi equals constant. And psi was, solution of psi was, we had it.
Now I'm even more interested in a drawing.
Okay, then that will be a homework. You have stream function and you just need to, so this is y part is here psi naught e minus ky plus ikx. So that's it. And that you take real part of it, cosine kx times e minus ky is constant. That is streamline. Let's go up. Your homework. Okay. See you next time.
Thank you.
Bye.
Hello.
Thanks.